3D printing, also known as additive manufacturing, has transformed the way products are designed, prototyped, and manufactured. This technology allows the creation of complex, custom objects layer by layer, offering unprecedented flexibility and creativity in production. Originally developed in the 1980s, 3D printing was initially limited to specific industries and high-cost applications. However, recent advancements have made it more accessible, affordable, and widely applicable across various sectors. At its core, 3D printing builds objects by depositing material in successive layers, each layer precisely calculated and controlled by software. This approach is fundamentally different from traditional subtractive manufacturing, where material is removed from a larger block to form the desired shape. Through additive manufacturing, designers and engineers can produce intricate structures, reduce waste, and achieve a high degree of customization. What is 3D printing? 3D printing, or additive manufacturing, is a technology that creates physical objects from digital models by adding material layer by layer. Unlike traditional manufacturing methods, which often involve cutting away material from a solid block, subtractive manufacturing, 3D printing builds objects from the ground up, depositing material in precise, ultra-thin layers until the desired shape is formed. The 3D printing process starts with a digital design, usually a 3D model created using computer-aided design (CAD) software. This model is then processed by a slicing software, which divides it into horizontal layers and generates instructions that the 3D printer will follow. The printer then uses materials such as plastics, metals, ceramics, or resins to create the object layer by layer, following the model's exact specifications. How 3D printing works. ChatGPT.noi. ChatGPT 3D printing works by creating objects layer by layer from a digital model, following a process known as additive manufacturing. Here's a breakdown of the steps involved in 3D printing. 1. Creating the 3D model design. The process begins with a digital 3D model, typically designed using computer-aided design (CAD) software. This model represents the exact shape and dimensions of the object to be printed. File preparation. The 3D model is saved in a file format that the printer can read, most commonly the STL, Standard Tessellation Language, or OBJ file format. These files contain detailed data about the object's surfaces and structure. 2. Slicing the model. Slicing software. The 3D model is loaded into a slicing program, which divides the model into thin horizontal layers. This software generates a set of instructions for the 3D printer, known as G-code, which guides the printer's movements and processes. Layer thickness. The thickness of each layer is critical. Thinner layers generally result in finer details and smoother surfaces, but take longer to print. Typical layer thicknesses range from 0.1 to 0.3 millimeters, depending on the desired quality and the printer's capabilities. 3. Printing process material selection. The 3D printer is loaded with the appropriate material, such as plastic filament, resin, metal powder, or composite materials. Different 3D printing technologies support specific materials and affect the final product's properties. Printing method. There are several methods, each with unique processes. Fused deposition modeling, FDM. The printer heats and extrudes thermoplastic filament through a nozzle, building each layer in a controlled manner. Stereolithography, SLA. A UV laser or light source cures liquid resin layer by layer, solidifying it to form the object. Selective laser sintering, SLS. A laser fuses powdered material, such as plastic or metal, layer by layer to create a solid object. Metal 3D printing. Methods like direct metal laser sintering, DMLS, or electron beam melting, EBM, use high-powered lasers or beams to melt metal powder. 4. Layer by layer construction. Layer formation. The 3D printer follows the G-code instructions to build the object one layer at a time, adding material layer upon layer. The print bed, or the printing mechanism, adjusts slightly between layers, allowing the structure to grow vertically. Adhesion between layers. In many 3D printing methods, each new layer partially melts or adheres to the previous one, creating a cohesive structure. This is a key aspect of achieving structural integrity in the finished part. 5. Post-processing. Cooling. After printing, the object may need time to cool and solidify fully, particularly in metal or resin-based printing. Finishing touches. Some 3D printed parts require additional post-processing steps, such as removing support structures, sanding, polishing, or painting, to achieve the final appearance and function. Quality control. For critical applications, printed parts undergo quality checks, such as inspections for defects or precise measurements, to ensure they meet the required specifications. Conclusion: 3D printing has transformed manufacturing with its flexibility and ability to create complex designs. The process allows rapid prototyping, on-demand production, and intricate customization, making it an invaluable tool across various industries, from automotive to healthcare. Benefits of 3D printing. 3D printing offers a range of advantages that make it an attractive option for industries and individuals alike. Its unique capabilities have the potential to transform manufacturing processes and product development. Here are some key benefits. 1. Cost effectiveness. Reduced production costs. Traditional manufacturing often requires expensive molds and tooling for production, especially for small batches. 3D printing eliminates the need for such tools, significantly lowering the initial investment. Less material waste. Additive manufacturing uses only the material necessary to create the object, minimizing waste compared to subtractive methods that cut away material from larger blocks. Economical prototyping. Companies can produce prototypes without the high costs associated with traditional manufacturing, allowing for more iterations and improvements without breaking the budget. 2. Time efficiency. Rapid prototyping. 3D printing accelerates the product development cycle by allowing designers to quickly create prototypes and test them in real-world conditions. Faster production cycles. With the ability to produce parts directly from digital files, lead times are significantly reduced. This speed is crucial for industries that require quick turnaround times. On-demand manufacturing. Products and parts can be printed as needed, reducing the time spent on production planning and inventory management. 3. Customization and design. Freedom complex geometries. 3D printing enables the creation of intricate and complex designs that are difficult or impossible to achieve with traditional manufacturing methods. Personalization. Products can be customized to meet individual customer specifications without significant additional costs, making mass customization feasible. Design flexibility. Changes to a product design can be implemented quickly by modifying the digital model, allowing for continuous improvement and adaptation. 4. Sustainability. Reduced waste. By adding material only where needed, 3D printing minimizes excess material usage, contributing to more sustainable manufacturing practices. Energy efficiency. Some 3D printing processes consume less energy compared to traditional manufacturing methods, leading to a smaller carbon footprint. Localized production. Manufacturing products closer to the point of use reduces transportation emissions and supports local economies. 5. Accessibility. Democratization of manufacturing. The availability of affordable desktop 3D printers allows small businesses, startups, and hobbyists to engage in manufacturing and innovation. Educational advancement. 3D printing serves as a powerful educational tool, encouraging learning in fields like engineering, design, and science through hands-on experience. 6. Supply chain simplification, inventory reduction. Companies can adopt a just-in-time manufacturing approach, printing parts as needed and reducing the need for large inventories. Simplified logistics. Digital files can be sent anywhere in the world for local production, minimizing shipping costs and complexities. The benefits of 3D printing are reshaping how products are designed, produced, and distributed. Its ability to offer cost savings, speed, customization, and sustainability makes it a transformative technology with widespread implications across various industries. Conclusion: 3D printing has emerged as a transformative technology, reshaping traditional manufacturing and opening doors to new possibilities across diverse fields. With its ability to create complex, customized objects directly from digital designs, 3D printing has already made significant impacts in industries such as healthcare, automotive, aerospace, consumer goods, and architecture. Its unique advantages, cost savings, rapid prototyping, design flexibility, and waste reduction are pushing boundaries and encouraging innovation at every level. However, 3D printing also faces challenges that must be addressed for it to reach its full potential. Material limitations, production speed, regulatory hurdles, and quality control issues remain obstacles in scaling 3D printing for mass production. But as technology and material science continue to advance, these challenges are expected to lessen, paving the way for broader adoption and more sophisticated applications.